Where is everybody?
They're all ready to skip.
Okay, so you have a quiz that is due at the beginning of class. So you have that for me? Please turn that in. How did it go? It was all right? Long? It was long, yeah. Okay. I don't have a stapler. I don't believe there's one. There's probably one. Do you have a stapler? $1 a staple over here in the corner, or across. There's a lab across the hall. Okay, thank you. Okay, thank you. Okay, anybody else? All right, all right. Thank you. Okay, thank you. All right. Okay, thank you. All right. We ready? Last call.
I forgot the actual quiz paper at home.
It's got to be stapled. They're selling staples over here for I think they're 50 cents a piece. That's not my stapler. You have to ask him, how much are you charging? Are you giving the staples away for free? Okay.
So do you need the front page?
I don't need it, but
He's like, I'm gonna take you.
I just need your work. As long as it is neat, stapled, and in order. That's what I asked for. $20 staple?
Robert,
What's up?
I left like a big mess on the board.
Okay. Okay.
Courtesy thing, I'll be back.
All right. All right, let's go. Come on, it's already 11. It's 1:03. Let's go. Okay, thank you. Okay. Everybody good? All right, so I wanted to start off just letting you all know that I appreciate all the I'm very excited to be here instead of being in a hospital worried. All right, so thank you again for all the support that everyone's expressed. All right, we get to start something new today. Now, what's kind of weird about this is I'm going to be combining several sections together because, well, there's parts of certain sections that we need and then other parts we don't need. And so I'm just kind of picking certain things. Now, you'll have a homework assignment. At some point, I'll give you a homework assignment here. Let me look. Well, but I'll tell you what section to look at and what problems to do. All right, so let's change gears. We've been doing integration, you know, all these different techniques. We've seen how involved it can be. Well, let's go back to something very fundamental. And that would be, let's think of this historically, all right? Human beings at some point needed to measure how much stuff was inside of some two-dimensional object. So you might think of this like, at some point, humans, and we're not going to get into like religious talk or philosophical talk or anything, okay? Hopefully you agree that at some point human beings said, like, this is my land and that's your land and you stay off my land, right? I mean, we like started to have borders, right, at some point. And so it became important to actually measure how much stuff you had, how much land you had, right? So we knew for a long time how to measure the area of a rectangle, right? So the area of a rectangle, we have a formula for it, and we all have to start this discussion by agreeing that area is length times width, right? So whatever, width, length, it doesn't matter how we label those. The area is length times width. But not everything is rectangular, right? So what if you have an object that's you know, shaped like this, right? Maybe that's your land. How do you measure the area of that? How do you do it? I don't know, right? I mean, that was the problem. How do you measure this? How do you figure out how much stuff is in here? Well, if we have straight edges, it's a little easier. Let's say we had some property that looked, I don't know, like that. That might be a little bit easier to measure the area. And the way we might do that is, I don't know, maybe break it up. Maybe we can draw a rectangle there and then maybe a triangle here and then maybe another rectangle in here. You see that? So I could kind of like break it up into two triangles, two rectangles and measure the area. So even with the shape like this, as long as I had straight sides, I could do something, or we could do something. But this was still a problem, right? And this is a problem that eluded us for a long time, all right? So one of the most fundamental shapes that we have that's difficult to measure the area of is a circle, right? So let's just take a circle. This is even more complicated than a circle, but let's see if we can't do something with that. So if we were trying to find the area of that, what would it be? What's the area of a circle? So you've seen this formula, right? Pi r squared, right? So that formula came from somewhere, yes? We will prove later on in this class, we will prove where this formula comes from, all right? We'll actually show that the area of a circle is pi r squared. But before this formula existed, how did they actually come up with it, right? How did they generate the formula? So the Chinese were the first to really go after this. And what they did was, see if you can agree with this sort of approach. They said, all right, we're trying to figure out the area of a circle. We can measure the area of rectangles without much problem, right? So they came in here and they would draw a really precise circle, all right? So they would get like a string and then some sort of scribe or something. They would draw a really, really precise circle. And then they would go in there with straight edges and they would draw some very precise rectangles. And they would be able to measure the area of this, right? So they know the area of that. And then they would draw maybe another rectangle in here. Maybe they'd try and squeeze another one in there, and maybe in this corner they'd squeeze a couple of little rectangles in there, and they'd be sitting there measuring those and getting the area of all of those, all right? And so as they did that, they would take all those blue areas and add them up. Now when we do this, we're going to have some error. Okay, we're going to have error in this. The error is going to be all these little corners that are not being picked up by the rectangles. Agreed? So what the Chinese did is they said, all right, let's take all these blue rectangles, and let's add them up. And we're going to get some approximate area, right? Let's call that A low. Okay, so if I added up all these rectangles, That would be an approximation to the area, but it would be too low, right? That would be too small. It's not quite the area. The area is a little bit more than that, right? Okay. And then they'd say, all right, let's start over. And they would draw the circle again. Very precise. And this time, they would draw a square on the outside of it, like this. Now, the area of that square is too much, right? That area would be more than the real area. So then what they would do is they would draw rectangles in here, and they would start subtracting that from the area of the big square. Make sense? And they would have error here also, right? They would have little corners that they didn't get. So if they took this square, took its area, then subtracted all these little rectangles, that area would be too much, wouldn't it? Would you agree? So that we'll call that area high, all right? So that area is too high, this one's too low. So they knew that the true area, the true area was somewhere between there, right? Right? If this one's not enough and this one's too much, then the true area has to be somewhere in there. So what they would do is they would draw a better circle with smaller and smaller rectangles, and they would just continue to get a better and better answer here and here, and they'd start to squeeze the true area between two smaller, basically your margins of error start to get smaller. So imagine this, drawing this with like hundreds, if not maybe thousands of rectangles in here. Yeah? They have a name for this method. This is called the method, you're going to love this name, of exhaustion. That's what it's called. Because it is exhausting, right? Imagine somebody sitting there measuring out all these little rectangles, trying to come up with this true area. It's exhausting to do this. You spend, months drawing these things. But the Chinese were able to figure out a relationship, and what they determined was that if you take a circle and you know this distance, which we know, we call it the radius, they said that the area is approximately 22/7 times the radius squared. Now 22/7 is well, if you get your calculator out, it's about 3.1 something, right? Pi is 3.1415, but it's non-repeating, non-terminating decimal. So it goes on forever, there's no pattern in it. 22/7 is actually called a rational number. So it's going to either have a pattern in it, or it's going to start repeating itself, something, or it's going to stop. So this was an approximation, and 22/7 is a really good approximation for pi. Like, you can use that, all right? They really didn't even know what pi was at this point. Understand? But they got that through the method of exhaustion. All right, do you get the idea? If we're trying to find the area of something, we can approximate it by filling it with things that we do know how to measure? Yeah? Okay. Now that idea didn't go away for a long time, all right? And it wasn't until calculus that we were actually able to figure out the true area of objects that have weird shapes. So let me try and walk you through this. Riemann is a mathematician who was the first one to really use the calculus to figure out areas. All right, and so we give him the name, we use his name when we talk about this topic, and we call it Riemann Sums. Sum meaning adding things up, right? So we've already talked about how do you measure the circle. Now, I used rectangles, didn't I? You could also, if you wanted to, you could do triangles. Like, you could start putting triangles in here. You can measure those. You could have more triangles, right? So check that out. That's a bunch of triangles, right? And I have some error. See, it's kind of hard to see the error here. Not going to be able to zoom in enough. Let me go back. Bring this back. There you go. You can see the error that I have, right? I'm going to have a bunch of error. But if I do more triangles, right? The more triangles I do, the smaller that error becomes, right? And the idea here is that if I could somehow wrap my head around the idea of having an infinite number of triangles, then I would have a true area, wouldn't I? But what's wrong with that idea? I mean, what's in conflict here? If I have more triangles, right, I'm going to have smaller area. But if I have more triangles, what's going to happen to this angle here? Right? The more triangles I add, what happens to the angle between each triangle? Yeah, it gets smaller, right? So look, here are some bigger triangles, right? So each triangle has a certain angle in here. So if I start adding more triangles, I'm going to have smaller and smaller angle. And if I tell you to shove an infinite number of triangles in there, then what's going to happen? What's going to happen to that angle? It's going to go to what? It's going to go to 0, isn't it? And can you actually have the area of a triangle if you have an angle of 0? Right? You can't. Does that make sense? It's like we would like to put an infinite number of triangles in here, but when we try to do it, we get triangles that become 0 angles, so we have nothing to measure anymore, right? It's like if I tell you, like what's the area of a string? It doesn't have area because it's one-dimensional. That makes sense? So we have this conflict. We have this problem. All right, I'm going to skip over this. We don't need to talk about that. So let's talk about a function, all right? So we'll get to the circle. We'll get back to the circle. But if we just take an arbitrary function, just give me some arbitrary function. And if I would like to know, let's say this is called, we'll call that A and we'll call that B. If I'd like to know what the area is below this function down to the x-axis, then one approach that I could use is to approximate it with rectangles, right? So think about this. Here in this picture, I've taken this graph right here, and I've cut this graph up so that I have placed 5 rectangles in this picture, right? What I did was I walked out a certain distance, I went up to the function, figured out how tall the function was there, and then I drew a rectangle over and down. And then I walked out by the same amount here, went up to the function, over and down, drew a second rectangle. And then I moved over by the same amount, up, over, down. Yes? Now, if I add up rectangle 1, 2, 3, 4, and 5, is that area too much or not enough? It's too much, right? We have a bunch of error in here. Like this right here shouldn't be here, that shouldn't be here, that shouldn't be here, that shouldn't be here. So how could I get a better approximation? Like if that has a bunch of error in it, how could I get a better approximation to the true area? Smaller rectangles or more rectangles, right? Which would be the same as having smaller rectangles. And that's what Riemann said he wanted to do, okay? He said, all right, what we're going to do is we're going to take a function, right? So here's a function. I'm going to walk out a certain amount, go up and over and draw my rectangle and do that. Just keep doing that until I get to the end. Then I'm going to add up the area of those. And then I'm just going to start putting more and 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 more, right? And that approximation is going to be really close to the true area. And Riemann said, gosh, is there a way that I can let the number of these go to infinity? Can I let the number of rectangles become infinite? And we run into the same exact problem that we just talked about. If I have an infinite number of rectangles, then what happens to their widths? They go to 0. And then if you have a rectangle, like it's kind of a ridiculous question, right? Like I have a rectangle here, this is 0 and that's 5. What's the area? You know what I'm saying? Like that doesn't make sense. But this is where calculus comes in. In calculus, we have this idea called the limit, right? The limit. The limit is all about letting something approach something without actually having to get there, right? That's in Cal 1. He said the limit as x approaches 2. You're approaching 2, but are you ever 2? No. So can we approach infinity without actually getting to infinity? Same idea. So Riemann was able to harness the power of the limit to actually get the true area, and that's what we're gonna do. All right? You kind of get the idea here, what's happening? All right. So let me go back to this screen. All right, let's see if you can follow this. First, let me get something out of the way. Sigma notation, just in case you've never seen it. Sigma notation. So there is a Greek letter, capital Greek letter S, that's capital S in Greek. All right, that's sigma. And we use this notation in math whenever we want to represent repeated addition. And here's how it works. What you do is below the sigma, you put what we call the index. A lot of times we use I here. And what you do is you give it like a starting number. And normally you're either going to start at 0 or at 1. And it just depends on what you want to do. So I'm going to start it at 1. And then up on the top, you put another number, and this tells you where to stop. So let me just make up a number here. Let me make it n, all right? Like that. So then to the right of this sigma notation, you place an expression. And that expression can be anything you want it to be. So let me just put an expression over here. I'll put I squared plus 1. And this I I'm using is not the imaginary number. Don't think of it as I like square root of -1. We're not talking about imaginary numbers here, all right? So I have this notation that says I'm going to somehow add things up. That's what this means. I'm going to add things up. Here's what I'm going to add up. I'm going to start by replacing I with 1, and then I'm going to stop when I get to n. So what this would be equal to is first you plug 1 in. So what happens when I plug in 1 here? I get 1 squared plus 1, that's going to be 2. So I get 2, right? Then I say plus. Now what I do is I let the index go up by 1. So now I'm going to plug in 2. So if I plug in 2 into that, what happens? What do I get? 5. And then plus, and now I plug in 3. 10. Plus, let's go one more. 4. 17. And then plus, and I'm going to keep on doing this, right? And then I will stop when I get to what? N. So if I plug n into that, what would I get? N squared plus 1. So all this notation is a condensed way of writing a really long sum. All right, it's just short. It's a shorter way of writing a bunch of things out. Understand? I know some of you have already seen that, but I just want to make sure everyone understands. When I'm about to put that up there, I want to make sure you know what's going on. Okay. Maybe you can help me on this one. What if I did 1 plus 3 plus 9 plus 27 plus 81? Can you write that in sigma notation for me? Can you come up with the actual formula I'm using there? And I'm actually going to force you to start your index at 1. Okay? Can anybody tell me what I would need to put here and where I would need to stop so that I would generate this list of, this sum?
81, the last number.
81 is the last one.
So 81 up. Or 80.
Well, it depends on what you put here. I'm willing to put 80 or 81 here. I don't care what. You can tell me I'll put it there as long as this formula here works. Does anybody recognize 1, 3, 9, 27, 81?
I squared minus 1.
Say it again.
I squared minus 1.
I squared minus 1. Will that work?
That would be 0 for.
Yeah, I squared. So let me just jot that down. You said I squared minus 1. If I plug in 1, I'm going to get 0 first, right? So not quite. What's that?
3 to the I minus 1.
3 to the I minus 1. So you notice that these are all powers of 3, right? This is 3 to the first power. That's 3 squared, 3 cubed, 3 to the fourth, right? Do you all see that now? And this one is 3 to what power? To the 0, because anything to the 0 is 1, right? So this is 3 to the 0. This is 3 to the 1. This is 3 squared. This is 3 cubed. This is 3 to the fourth. We all on board with that? So if I start at I equals 1, I actually need to be able to plug that in and get 0. So I put I minus 1, or you put I minus 1. So 1 minus 1 would be 0. I get 3 to the 0, which would give us 1. Plus, now I plug in I is 2. 2 minus 1 is 1. So you get 3 to the first power. Are y'all seeing that or not? Plus, now where do I stop, though? Like, what do I need to stop my index at here? This is 3 to the 4th, right? So I need to stop at 5, because 5 minus 1 will give me 4. Now, this is coming later. This is chapter 8. We're going to mess with this a lot, okay? I just wanted to see if you could go backwards on it, all right? You don't have to worry about this right now. All right, let's get down to the Riemann sums. What I'm going to try and do right now is actually pretty profound. We're going to be looking at the way Riemann tried to figure out what the area underneath the curve was and how he came up with the formula for it. And then you're going to see how that formula somehow is related to our integral. All right, remember the integral symbol and everything? All right, so let's start with this. Let's start with the function. So let's say that we have some function. Let's call that function f. And we are going to look at that function just between a and b. And what I want to know, or what Riemann was trying to figure out, is what's the area in here, okay? So that's the big question. What is area under f, right, and above the x-axis? Because imagine if we could do this, right? If we could find the area under this function, if we had a general formula for it, then if I drew this function, that is a function, right? If I could find the area under this, wouldn't I have a formula for finding the area of a quarter of a circle, right? And then all I'd have to do is basically multiply by 4 and I'd have the area of the true circle. So we can extend this idea to any function and get the area of a bunch of different shapes. So we're coming up with a general formula. All right, so here's what he did. He said, I'm not going to cut this. I'm not going to put one rectangle in here. I'm not going to put 2 rectangles. I'm not going to put 3. I'm not going to put 4. I'm actually going to put n rectangles in here. All right? And he's saying, I'm not going to tell you what n is. All right? So imagine that we put n equally spaced rectangles in here. So let's draw them. Okay, this is just for the sake of you being able to see it, okay? Call that rectangle 1, right? So I had to give it a little bit of width because, otherwise you wouldn't be able to see it sitting there. That's rectangle 1. This is rectangle 2, right? And I keep on doing that, and then my last rectangle over here is rectangle n. That's this one right here. All right? Is that all right? Do you agree with this statement? The true area underneath that curve is approximately R1 plus R2 plus R3 plus all the way till you get to R sub n. You can say yes or no. Do you agree with that? Okay. It's approximate. I'm not saying it is equal. I'm saying it's approximately equal to. All right. Now, can you rewrite this in sigma notation? Sum I equals 1. Where am I going to stop? At n, right? N. And this is going to be R sub I. That's just a condensed way of writing that sum out, right? Just a condensed way of writing this. Now, I would like to actually talk about the area of each of those rectangles. Okay, so let's start with rectangle 1. What can you tell me about the area of rectangle 1? What is it equal to? Now, this is going to be kind of weird, but just see if you can follow me on this. Isn't it going to be the width of this rectangle? Which we don't really know right now, do we? And then it's going to be times the height of the rectangle. Yes? So I'm just going to write that down. This is going to be the width of rectangle 1 times the height of rectangle 1. Now, how wide is rectangle 1? So I'm going to try and help you with this. I'm going to draw another picture over here, just to help us. Let's say instead of us going from A to B, what if I said we're going to go from 1 to 6? Okay, so instead of A to B, I go from 1 to 6. And let's say I cut this into 8 rectangles. 8 rectangles. So I've got some function here, and I do 8 rectangles in here. How wide is each rectangle? Let me see. 1, 2, 3, 4, 5, 6, 7, 8. There we go. They're all, now I have to tell you, they're all the same width, okay? They're all the same. So how wide would each one be? What's it? What is it? 5 over 8? Do you all agree with that or not? How'd you get that? Okay, so you looked at the distance from here to here, right? That's 6 minus 1? That's 5. So you got distance from here to here, 5, and you're going to cut it into 8 equal pieces, right? So you're going to divide that by 8. Agreed? So that would be 5/8. That would be the width of every single one of those, wouldn't it? Let's use that same idea over here. How wide would each rectangle be? Well, what's the distance from here to here? B minus A, right? Just like 6 minus 1, this would be B minus A. But then you divide that by what? However many rectangles you had, which would be n. So would you all agree with me that this right here, the width of rectangle 1, is B minus A divided by n, right? Any questions? Are you sure? Now, how tall is the function? Well, the height of the function for rectangle 1 is this. We're getting it off of that point, aren't we? It's that height. But that actually comes from taking this point right here, which I'm going to put a question mark on it. I'm taking that point right there and I'm plugging it into the function, right? And then that function is spitting something out. Now, I don't know what the function is. Nobody has told me. Is this like x squared plus 1? Is this sine x? Is this natural log x? Nobody's told me. But in general, if somebody were to tell me what this function is, to figure out the height, I would take this point, plug it into the function, and it would spit it out, right? That's my height. So could I call this height f of whatever that question mark is? Like this is like an x coordinate, right? You give me that x coordinate, plug it in, it spits out the height. Yes? Now, I'd like to know what that question mark is. So let's go back over to this one. Do you know what that first point would be? What would it be in this case? It would be 1, right? Here's 1, but then we would move over by how much? 5/8, right? So it would be like we start at 1 and then we add 5/8 to it, yes? Over here in this picture, it would be b minus a over n f of, okay, so we start where again? We started at 1 here. So here we'd be starting where? At a, and then we would add to that what? That jump, which here is 5/8, but over there it's b minus a over n. So it would be a plus b minus a over n. That is a, you know what? My notation sucks here. No, it doesn't suck, but I need to change something. I should have called these like area of rectangle 1, area of rectangle 2. But over here I did it. I said area of rectangle 1. So please change this to just rectangle 1. And everyone understand I'm talking about the area of it, okay? So the area of rectangle 1 is this. And so that goes right there, right? This expression right here, right, goes right there. But that was just the first rectangle. Let's figure out what the area of the second rectangle is. Are y'all kind of following me or not?
Yeah.
Okay. Where do I erase? I don't even know what to erase here. Let me do this. I'm going to get rid of this. I'm going to put this up here. Rectangle 1 was the area of rectangle 1 is equal to b minus a over n times f of a plus b minus a over n. That was the area of rectangle 1. Now, what is the area of rectangle 2? So if I go to my second rectangle, that's the point I'm talking about, right? That's the question mark. Now, how wide is it? What's the width of rectangle 2? Same thing as before, right? In fact, all of the rectangles will have the same width. The width of rectangle 1 is the same as width of rectangle 2, 3, 4, 5, all the way out to n, right? So this can go into the formula for all of those. B minus a over n. This is the part that's going to change. This is the part that's going to change. Okay, so let's go back to this picture because I think this picture will help us see where we're going to get this next point. We got this point by saying take 1 and add 5/8, right? But if we're going to move over to this point right here, now what are we going to, how can we look at that point right there? You could say, okay, start from here and add 5/8 again, right? Or, and this is the way we need to look at it, start from 1 and move over how far? 2 of these 5/8, right? 2 of them. And so it's like, to get this blue point, what we did was we started at A and we moved over by 1 of these, right? To get the height of rectangle B, we're going to take the function, we're going to start at A, but now we're going to add 2 of these b minus a over n's. So you can almost imagine that this one had like a 1 of these, and that told you start at A, move over by 1 of those. This one's saying start at A, move over by 2 of them. Yes? And that would move us over, well, over here, it would move us over from A, 1, 2 jumps, and then plug that into the function. That would get your height. What about the third rectangle? Are y'all seeing we're about to establish a pattern? The third rectangle has the same width, b minus a over n. F of a plus 3. So it's the same thing. We start at A, and this time jump over 1, 2, 3 of those jumps. B minus a over n's. And you get the pattern, right?
Yeah.
Okay. Next one, the only thing that would change in the next formula is what? This right here would change to a 4, right? So let's see. Let's keep going with this. How many rectangles do we have here? We have n of them. So this pattern would continue until we get down to the last rectangle, the nth rectangle. It would still be b minus a over n, but the last one would be a plus, how many jumps have we made at this point? We've made n of them, haven't we? So we've gone n jumps, b minus a over n. And look, for this last one, don't these cancel? And don't you get a plus b minus a? Which is just f of b. And isn't that last corner point that would go in and give you that rectangle? So if all of these things look identical to one another, with the exception of this thing right here keeps changing every time, then I can use my sigma notation and I can write it like this. The area, true area, is approximately the sum I equals 1 to where? Well, we're going to start out with 1, then it's going to go to 2, then it's going to go to 3, and I'm going to stop when I get to n, right? sum I equals 1 to n of, well, this is the same in every single one of them, right? So I'm actually going to throw that out on the back side, and you'll see why in a second. That's that common width of every single rectangle. And then this right here, f, is going to be f of a plus I times b minus a over n. Right there. Do y'all see how this actually generates all of these? You know, start out with I as 1, right? Replace that with 1, and then this becomes that one. Then you say plus. Now you let this be 2, and it's this. That's a 2 now. Everything else is the same. That gives you this one. Then you let I be 3, and then you just get this one. This one you go all the way to n. So that sigma notation will give you the sum of all of the rectangles, right? That's it. That's the general formula that Riemann was able to come up with. Now, this is still an approximation, okay? So now if somebody were to hand you a function, they said, hey, look, everyone, take a look at f of x equals x squared, and take a look at it on the interval 1 to 2. So you go graph it. Here's our parabola like this. If we went between 1 and 2 and looked at just the graph right here, and imagine trying to find the area of this, then if I want to use 100 rectangles in here, what I would do is replace that with 100, that with 100, that with 100. B would be replaced with 2, right? A would be replaced with 1, and then I'd actually have to compute all those things, all right? And that's, of course, it's tedious, right? But it's a very, very nice way of organizing all those ideas into one formula, right? All right, so we are not going to do Riemann sums by hand, all right? In some calculus 1 classes, some calculus 2 classes, we actually practice doing Riemann sums by hand at this point. Like, we actually do this. I say, here's a function, here's the interval, let's cut it into 20 rectangles using the formula. We'll just say, yeah, that sounds like fun, but we're not going to do it. All right, so we still have an approximation. We still have an approximation. So how do we get the true area? Now, we talked about this a second ago. Theoretically, how could I get the true area? Or how could I get closer and closer to the true area? More rectangles, right? More rectangles. Smaller, they're not as wide, right? So if I go smaller rectangles or more rectangles, then that'll get me closer to the true area. If I let the number of rectangles become infinite, then that should approach the true area, right? That limit should approach the true area. And so all you have to do to get the true area is one simple little thing to this formula. The true area is equal to the limit as n goes to infinity of Riemann's formula. There we go. So I take Riemann's formula and we let n go to infinity, and that lets us get the true area. So it would be almost impossible to ever calculate the true area, right? Because how are you going to have an infinite number of rectangles and add up all those areas, right? You're not going to be able to do it, right? You'll agree with that?
Yeah.
It's going to be a problem. But we know in calculus that sometimes when you take a limit, you know, sometimes you get infinity, sometimes you get 0, but sometimes you get a number like 4 when you take the limit of something. So it's very plausible that we could get nice answers. So this is the true area of underneath the curve, all right, underneath f between a and b. Now it wasn't until later that we actually were able to make a very profound step, or take a very profound step from this. And what we discovered, or what was proven, was called the fundamental theorem of calculus. The fundamental theorem of calculus. And as the title suggests, it is the fundamental result of calculus. It is one of the, if not the most important result in calculus. And what it does is it connects together the derivative and antiderivative in a formula. It somehow creates a relationship. Now, I'm not going to prove the fundamental theorem of calculus to you, all right? If you want to see the proof, you can come by my office and we can sit down, but it's going to take a lot of building up some other things first before we can do the proof. So there's actually like two versions of this theorem. I'm going to give you the one that we're going to use the most. And here's what it says. The fundamental theorem of calculus says this, that the area under a function f on the interval AB is capital F of B minus capital F of A, where capital F is an antiderivative of little f. Now let's try and understand what the heck this means. This is saying that if you would like to find the area underneath this curve, if you'd like to find that in between A and B, then all you need to do is calculate this quantity right here. And what's that quantity? Well, what is capital F? It's the antiderivative. So you need to find the antiderivative of this function first, which we've spent weeks doing now, right? And then all you do once you find the antiderivative is plug b into that function, right? B is a number. Plug it into the function, then plug a into that function, subtract the two. That numerical answer is the area underneath that curve. And that is the big result, all right? Is that the antiderivative gives us that area that we're looking for. Does that kind of make sense? Questions? Yes? That is the true area. So what it does is it actually, it's involving this limit, right? So it's actually letting us somehow use this limit and take the limit, and we can determine that this has to happen. It's, I don't know, it's a fundamental theorem. It is very important, all right? Now, I would like to somehow summarize this fundamental theorem of calculus with some new notation, all right? So how can I write this down? How can I write this theorem down in a mathematical sense? Well, we've already done antiderivatives, and I showed you the notation for that, right? I never really got too deep into where it came from. Well, let's see if this makes sense now. Since Riemann has his formula here, this right here isn't just a sigma, right? It's not just sigma. It's the limit of a sigma. So I need a special notation for that. So why don't I use that, okay? That is my symbol that lets you know I'm taking the limit of a sum. It's kind of an S, right? So it's not quite the sigma, but it is like an elongated S. All right, now what is it that I'm going to add up? Well, this is just the function, right, with some things plugged into it. So these things, all these little things that I did in here, these were all little x's, weren't they? I mean, they're little x values, whatever they were. So somehow I'm going to be taking the function and plugging some values of x into it. Yeah? And then I'm going to be multiplying this by that. Right? How can I represent that? Well, that right there was the width of each rectangle, right? And it was the same for every rectangle. So wouldn't you agree, or maybe you'll disagree, that this right here is my change in x? It's how much x changes on every jump right? That b minus a over n is like my little delta x, my little change in x. Yes? Now, delta x usually, it stands for change in x, but if I'm taking a limit, those little things, those changes are going to get, what, infinitesimally small? And so I don't want to quite just leave it as delta x. I want you to understand that the derivative, or the limit is involved, and these things are getting infinitesimal. So instead of using delta x here, that's delta, sorry, terrible delta. Instead of using delta x to let you know that the limit is involved, I'm going to put dx instead. All right? And so do you see now, this is what I showed you, this is the notation we use to find antiderivatives, but do you see how this right here comes from Riemann's formula right here? It's the limit of a sum, it's the function evaluated at all these different points, and it's always multiplied by this little differential, this little jump in x that you do every time. Now, I need a little more, because I need to somehow tell you that you're finding an area here. So what can I do to let you know that this is different than just finding the antiderivative? Oh, well, I can put an a here and a b here, and that will tell you, hey, look, this is different than you just going and finding the antiderivative. You're actually looking just on an interval between a and b, and that the answer to this right here, this notation, is actually this quantity, capital F of b minus capital F of a. And that's your area. Sorry, I should have put a out here. All right. What do y'all think? You don't like it? From now on, when you see integral signs, I want you to look at them completely different. When you see numbers here, I want you to be thinking about, hey, we're calculating something here, all right? This is going to give us a numerical answer. And I want you to investigate each piece of the integral. That right there is the height of the function, right? That is the height of the rectangle. This right here is the width of the rectangle. So what we're doing is we're adding up areas of rectangles. Agreed? Okay. As we go through the next chapter, you're going to see that we're going to be trying to find volumes of things. Not areas, volumes, and what's inside the integral is going to be completely dictated by what it is we're trying to find. If we're trying to find the volume of something, then this formula's got to change because this is the area of something, right? So volume, it's going to look different. All right, that's the fundamental theorem of calculus. I hope that all made sense. I hope that in some way shows you where this symbol comes from, why we use it, and now what we're going to do is just use it, practice it. Just apply the theorem. I'll give you a couple of examples, and we'll just calculate. All right? We'll start with a pretty simple example. All right, so if you were just explaining this to somebody in words, what is it that this is asking you to do? Find the area underneath the quadratic x squared, the parabola x squared, from an x value of 1 to 2. So this is the drawing that goes with this, which we don't need, is the one I had up here before, right? We're going to go from 1 to 2. And we're just looking at that little segment of the curve, and we're dropping it down to the x-axis, and we're going to actually find the exact area of that. According to the fundamental theorem of calculus, this is just capital F of b minus capital F of a, right? So what's capital F? The antiderivative of that, right? What's the antiderivative of x squared? 1/3 x cubed, right? Now, what we do, this next line that I write, or the next thing I'm going to write, is the standard notation that we use when we're doing these areas. and that is you write down the antiderivative right now. You just write it down. Okay? And then after you write the antiderivative down, you put this bar, and then you put 1 here and 2 here. So all this does is it helps you organize your ideas. You're saying, look, if I want to find the area under this curve, then first I need to find its antiderivative, right? There it is. Now, don't forget, you've got to plug 2 and you've got to plug 1 in. All right, so that's kind of like a placeholder that just, it allows me to write the antiderivative down. Now I'll actually do the next step, which is to do capital F of B minus capital F of A, right? That's the next step. So that means I'm going to plug 2 into this. What would I get if I plug in 2? 8 over 3. And if I plug in 1, get 1/3. And what's 8/3 minus 1/3? 7/3. The exact area under the function x squared on the interval 1 to 2 is 7/3. I am asking you to trust that the fundamental theorem of calculus is right. Okay, I am asking you to take that on faith, right? I didn't prove it to you. What do y'all think of this? What about when you took an antiderivative? I thought you had to have plus c out here. Okay, yeah, we do have values, so do we need the c? Well, think about this. What if I did put plus c here, right? Then wouldn't it be plus c here and plus c here? And then wouldn't this c and this c cancel every single time? Wouldn't they? So you never need to consider plus c when you're doing these. All right? Yes?
So then why do we have to put plus u whenever we just find the derivative?
Because when you're okay, this is a great question, okay? So that, I was just about to put this on the board, all right? The difference between what we've done and what we're doing now. The indefinite integral is what we've been doing. And that's the integral, this is the notation for it. And this just means capital F of x plus c. So if you don't have numbers written here, then what it's asking you to find is the general antiderivative, which would be the antiderivative plus some constant, because it gives you an entire family of functions. Compare that to the definite integral. That's the new word, definite integral. The definite integral is an integral, but now you have these numbers here, and that is equal to capital F of B minus capital F of A. This right here normally is going to just be a number, right? Whereas over here, your answer is a family of functions. So the indefinite integral gives you a family of functions. The definite integral gives you a numerical answer. Most of the time, we're going to see sometimes this is infinite, but it's not a family of functions. Some other notation or language. If you go back in your notes, we said this was the integral sign. We said this was the integrand. We called this the differential. This is the antiderivative. This is the constant of integration. These are all terms we've used, but we've never had a name for those. This one is called the lower limit of integration. And guess what this one's called? Yeah, the upper one. Upper limit of integration. The order that you do this is important, all right? You've got to go B in first, okay? So that means if you're looking at the number line, A is always the left right endpoint, B is always the right endpoint. This one goes in first, and then this one goes in second, and you subtract the two. You can't get them backwards. Now, if you do them backwards, you'll get the same answer, but it'll be off by a sign, right? It'll be negative instead of positive, or positive instead of negative. All right.